Okay, chapter 2, lots of important stuff here, a lot of which is underemphasized or just outright ignored in many American curricula, so we're definitely going to spend some time here. So this first video is just going to be about the first 5 sections, which is about sets, so something that you may not know too much about. And then the second video will be about Venn diagrams, which is one way to represent sets. And actually a lot of this stuff, even if you don't formally know sets, a lot of it is going to make sense. It just might be a new notation and a way of thinking about stuff. So section A is exactly what I'm talking about. There's really nothing that challenging in this section except for perhaps some new notation, new terminology. So take a moment and read through this, jot down notes where you need, because I don't have a lot to add here. I do just want to say a few things about the subsets and proper subsets. So first of all, proper subsets are what we tend to see more often, I think, just in interesting problems, because in this case, the two sets are not equal to each other, which is obviously a far more general case than when they are coincidentally equal to each other. So in this case, we have some number of elements in set A, and we have some number of elements in set B, but we know that every single element in A is also in B. And what that tells us is that set B is larger than set A. It has more members in it. And you can kind of see the symbol there looks almost like a less than sign. Right? So that's how I try to keep track of which way does this proper subset symbol point. The two prongs are going towards the larger of the two sets, the one which contains the other one. And one other thing I'll say is if it's true that A is a proper subset of B, then we could also reverse that and we could say that B is a proper superset of A. So a superset is the opposite of a subset. That terminology doesn't show up in our book, but it's out there, so I thought I'd share it with you. Let's look at this in practice, and you'll see that this is pretty simple stuff. So in this example, we have a set P, which is all the letters in the word amateur, and then we have a set Q, which is all the letters in the word team. So for part A, if I wanted to list the elements of P and Q, I'm just going to say P has those letters and Q has those letters. Notice that we do not include that second A twice when we're listing out the members of the set. All of the members of the set must be unique. Part B, find, this notation means the number of elements in P. Okay, we count them. There's 6 in P, and then we count for Q, there's 4 in Q. So that's very, very easy. Part C, is U an element of set Q? So I look at this list of numbers, I don't see the letter U, so that's false. Is R not an element of set Q? I look at this set of letters again, R is not there, so that makes that statement true. Now we get into subsets and proper subsets. I should have said this on the last page. Notice here we've got the horizontal line there for just subset, and that tells me that the two are going to be equal. Obviously, we know that they're not equal. I mean, we can see that right down here. So this one is definitely going to be false. But let's see. Is it true that Q is a subset of P? So do I see, a proper subset? Whoa. Do I see all 4 of these letters also in set P? Yes, T, E, A, M spells T. So it is true that Q is a proper subset of P. We move on to section B. Just a few more vocabulary words and a few new pieces of notation here. So we have the intersection of two sets is all the elements that are in both of them. And we use this notation for that. I like to think of that symbol as being like the letter N in the word intersection. Compare that to down below. We have the union of two sets are all the elements that are in either A or B. And our symbol for that, that looks like a U clearly for the word union. It's important to note that mathematically, this word or, it implies or both. So if something is in both A and B, it is in the intersection of A and B, but it is also in their union. Okay, in math, anytime we see the word or, it automatically means or both. And finally up here, if two sets don't have any intersection, there's nothing in common, then we say they're disjoint or mutually exclusive, and we can use this symbol to represent that. So down below, we've got two more examples. Now the sets are made up of numbers instead of letters. M intersection N. So we look for all of the elements that are in both of these. I see a 3 is in both of them. I see a 9 is in both of them, and that's pretty much it. And then for the union, that's going to be every element that's in either M or N. But just like before, we're not going to repeat anything. So the numbers 3 and 9 are only going to show up once in this union, but otherwise we have every single number appearing in either of those two lists. Okay, section C, we're moving right along here. And by the way, these sections are all really short and they just don't have anything particularly unique or interesting to offer. So that's why I'm just forging ahead here. It's not like I'm skipping over a lot of stuff at your expense. Okay, section C. When we see U, that's the name for the universal set. That's like the whole universe. That's everything possible within the context of whatever question we're looking at. The complement, spelled with an E, not with an I. So just like a complementary angle, or two complementary angles add up to 90 degrees. The complementary sets are two sets which, when put together, give us the universal set. And the notation for the complement of A is that right there for the IB. There's many other types out there. You might see that. You might see that. There's lots of notation out there, but on our exams and in our textbook, we're going to see the A with the little apostrophe next to it. When spoken out loud, I might call that A complement. I might call that not A. I might call that A prime. Within the context of a set problem, if I say any of those words, I mean the same thing, the complement of A. Okay, just thinking about complements down below, obviously the set and its complement, they must have no intersection because they have no common members, because put together they make the universal set. The union of the two of them is the universal set. And finally, the number of elements in set A plus the number of elements in A complement has to give us the number of elements in the universal set, provided that the universal set is finite in size. And that's very important because on the very next slide, we're jumping into section D already, which is going to deal with infinite sets. And this is where set theory really gets interesting. So far in the few examples we've seen, sets have just been lists of letters or numbers. Now, a set could be made up of words. It could be made up of people's names, countries, colors. It really could be anything in the set. But the most important, or I think the most important type of set that we're going to look at are sets of numbers, specifically these infinitely large sets of numbers, which I'm sure you are familiar with. So first, we've got the natural numbers, which in the International Baccalaureate is defined as starting from 0 and then the positive integers. 0, 1, 2, 3, 4, etc. I know in American curricula, natural numbers tends to only mean from 1 and above, and then we use the word whole numbers to include 0. In this course, natural numbers starts at 0. You need to know that symbol. You absolutely need to know that that symbol represents that set of numbers. Likewise, we have the integers, which are just the natural numbers, but then we include any of their opposites. You absolutely must know that symbol. And then another popular one we see in many IB questions is if they just want to list the positive integers, so that's the natural numbers but without 0, they'll use the double Z there, but with a little plus. Continuing on, we have the rational numbers represented by a Q. Rational meaning that we can write them in the form of a fraction. And that could be either, they could look like fractions, they could look like improper fractions or mixed numbers. We have repeating decimals, and we have any type of square root which can be simplified. The irrational numbers, so here's our complement. We use Q prime. And so that's going to be any type of square root that's not a perfect square. And there's a proof for that out there, but I won't go into it here. Pi is a very famous irrational number. Later on in this course, we'll get into E if you're not familiar with that one. Also, other types of radicals. So for example, like the cubed root of 9, that is irrational, and so on. And then beyond these sets, we have the real numbers, which is really the union of the sets we've just described. That is the union of the rational and the irrational make up the reals. Because of course, everything that we saw on the previous page, the natural numbers and the integers, those are all contained within the rational numbers. All right, and now just to help us visualize these for a moment, here is a diagram. It's not a Venn diagram, but it is a diagram nonetheless, just to help us visualize what's going on here, and to see what sets are contained within the others. And we see that the rationals and the irrationals put together make up the reals. But of course, there's more to the story. Later on in this course, we will look at imaginary numbers, which were actually referenced on the previous page. So things like the square root of -2 was an example on the previous slide. That's an imaginary number. When we put imaginary numbers and real numbers together, we get things called complex numbers. So they're going to be in the form of a plus bi, where we have a real part and an imaginary part. But the story doesn't end there. Beyond that, we have other things. Quaternions, octonions. These are definitely not part of our course, although I'm sure I will not be able to help myself. When we study complex numbers, I will certainly mention how they extend to other further number systems. But you don't have to worry about them here. And really, you could go through a full math major in university and not come into contact with any of that stuff. It's a little niche. And there's other types of number sets out there. So we didn't talk about prime numbers and composite numbers, but those are two different infinitely large number sets. Odds numbers and even numbers, you know what those are. Constructible, algebraic, computable, transcendental numbers. Feel free to look those up if you're interested in more types of numbers. That's all very interesting stuff, but definitely beyond the scope of this course. And then we have, of course, things that are just not numbers, such as this made-up thing here. And I include infinity very intentionally because infinity is not a number, and we need to correct anybody who pretends that it is. Also, 2 slides back, you saw 1 divided by 0 as an example of something that could not be put on the number line. And that is because, well, 1 divided by 0 that's not a number. It's not defined. You can't divide by 0, and you can't divide by 0 because it's basically infinity or negative infinity. But that's a discussion for calculus once we get up to that. And I don't know, if you can come up with something else that should have made this list, please let me know in the comments. And that brings us to the final section for this video, E, where we'll look at some number sets and figure out some better ways to express them. Because we mathematicians are lazy, we don't want to write down things in words. Sentences just get to be too long and unwieldy. So in the first example, we want to describe this set. On a number line, it's just represented by the 7 dots on that number line. if I wanted to write that in a sentence, I could describe it as the set of all integers x such that x lies in between -3 and 5. And between, in this case, it's not necessarily clear from the phrasing here, but that's between -3 and 5, and I would say exclusive, meaning this excludes -3 and 5 from the set. You could have said between -2 and 4 and then said inclusive, and then we would have known that -2 and 4 were like the boundaries. So that's one reason that we don't like words right there. That phrasing right there is confusing. So the way that we'd write it out in symbols is right here. So we start off by noting that x is going to be an integer, and then we draw a little vertical line, which is understood to be such that, and then we have x is in between -3 and 5, and we're using less than symbols rather than less than or equal to indicate that -3 and 5 are not included. We could have used -2 and 4 and included them like that. We could have been real jerks and said something like -2 and 5 like that. That's still correct. And we could have switched it around with -3 and 4 if we wanted to as well. Don't do that though. Be cool, guys. Come on. Down below, we've got an example where it's not integers, but it's just real numbers. So now we can't even put the dots on the number line because there's actually an infinite number of real numbers in between -2 and 4. So what we do is we put a dot at each end and we just connect them with a line like we see here. When the value is included, we fill in the circle, and when the value is not included, we leave the circle unfilled in. They call it an open circle, whatever. Now, in this case, we could start off by noting that x is an element of the real numbers. However, we commonly just leave that part out and we just say x such that x is in between -2 and 4. In fact, I would say that we even leave out that first part pretty often. And so if we were to just write that, -2 less than or equal to x less than 4, it would be implied that that means x is a real number. So it's really important if you're trying to write down for a set when it's not a real number, such as the first example, you definitely need to include that part there so that the reader knows what set of numbers you're referring to. And you can do that using symbols, or you could do it in words as well. So just more about how we can symbolically notate these various intervals. We've got basically 3 ways to do it. We can do it with the number line as we just saw. We can do it using brackets and inequality symbols like we just saw. Or as a third option, we use square brackets is what the IB uses. However, I recognize, again, that many of you coming from an American curriculum will not be familiar with when the square bracket points away, such as here. So some people will know to use rounded brackets when an element is not included. That's fine. You are allowed to write it like this. However, any question in our textbook and any question in an exam is going to use the square brackets pointed away from the number if it's not included. But you are allowed to use any mathematical notation that is common enough to be understood, and that certainly is common enough to be understood. Okay, and again down here we see infinity is not a number, so infinity is not included when we want to say that x is greater than or equal to some particular value a. So our universe in this question are all of the integers in between -5 and 5 inclusive. So we got to start by noting what the possible universe is in the problem. All right, now the first 2 are going to be easy. List the elements of A and B. So just looking what we have here, A is going to be 1, 2, 3, and 4. B is going to be -3, -2, 1, -1, 0, and 1. Notice here it was equal to -3, but not equal to 2. Next to not A and not B. So we have to think just a little bit harder about this. We're going to list out all the elements in between -5 and 5, which were not here. So that's going to be from -5 to 0, but also 5. And then all the ones that were not here. So -5, -4, and then 2 and above. Letter E is going to be the intersection of A and B. So what numbers do we see showing up in both of these? Really just the number 1. That's the only thing that's going to be in the intersection. Whereas the union, which will be letter F, that's going to be all the numbers put together. So that's going to be from -3 all the way up to +4. And again, we do not repeat the number 1. It only shows up there once. And then for not A intersect B, now we're just going to compare two different sets. We see that they both have a 0. Actually, we see that they both have 0 through -3. So that's going to be our intersection for not A and B. And then letter H is going to be our union of not A and not B. And that's going to include pretty much everything except for, as we look at these two lists, what number is missing. Here we're starting at -5 over here, going all the way to 0. Here we skip 1, and we just have 2, 3, 4, and 5. Notice that that 1 was exactly the value that was in the intersection of A and B, and that is not a coincidence. The intersection of A and B is always going to be equal to the union of not A and not B. But that proof is going to be left for another day. We're going to call that video right here. If you're really excited about sets, please do check the link in the video description for another video about Russell's paradox, the most famous set theory paradox that I could think of, put forward by Bertrand Russell, who is a British philosopher, mathematician, and logician who lived in the 1800s and 1900s. Russell had a lot to say about mathematics throughout his career, but I thought that for today's video I would end with this particular quote of his that really grabbed me when I first saw it. And I think that you're either going to hear this and say, oh yeah, I totally get that, or you're going to be utterly confused by what he's talking about. And so Bertrand Russell said, I like mathematics because it is not human and has nothing particular to do with this planet or with the whole accidental universe. Because like Spinoza's God, it won't love us in return.